So I'll be the one talking about blockchain. I'm sorry about that. But obviously you're in the room, so you're not completely skeptical, or maybe you are extra skeptical and you want to hear something talk about some of your skepticism. So I will be talking about the blockchain, I will be talking about Bitcoin, I'll be talking a little bit about Ethereum and about some of the alternatives about that stuff. But first of all, I'd like to get just a rough feeling of where you folks stand on all these issues. So how many of you own a cryptocurrency like Bitcoin or something else? That's a few. How many of you have explained what the blockchain is to their friends? How many of you have written an Ethereum smart contract? 2 people. Who has no idea what this blockchain thing is about? Okay, that's a nice mixture. So, we're going to have a distribution of work here. Some of you will be learning about the blockchain, some of you will be annoyed at me making mistakes. So feel free to interrupt at any point in time. I'm absolutely happy about discussions. I've done this talk a number of times. I have zero ambition to get through all of my slides. I don't care at all. If you interrupt me and ask interesting questions, we'll make this completely interactive. If you don't, I'll just keep talking for 45 minutes. So, let's talk about this blockchain thing. I wanted to start with the oldest and, at least for now, most mature implementation of this particular approach, which is obviously Bitcoin. So we're not going to be talking only about this, but it's going to take some amount of time, and I'll be using it to explain some of the core concepts. We'll get to other platforms as well, but it's I think one of the interesting things because it sort of originated the whole concept. So everybody here has heard about Bitcoin. There's no chance to avoid it, even if you're a normal person and not a nerd like us. But it's still interesting to take a look at some of the roots of the whole thing. So first of all, you could argue that Bitcoin is the first practical application of cryptography to a certain set of use cases, or to a certain use case with a set of restrictions and requirements around it. The idea of Bitcoin, as is very similar to most of the other blockchain installations or platforms, is to maintain some sort of immutable history, immutable database, immutable ledger, if you want, of something. In the case of Bitcoin, it's a history of transactions. And the cool thing here is that it's maintained with guaranteed consistency, so we have one state of the world that everybody agrees on, at least after a certain amount of time and to a certain degree of probability. And they do that without relying on any centralized instance. So there is no bank maintaining an account for you. There is nobody who you can go to if something goes wrong and ask them what the actual situation is, because there is just one truth, one thing that everybody shares and that everybody looks at. It's very resistant to any sort of forgery and fraud, although I'm sure you've heard about all the criminal activity surrounding Bitcoin and about all the things that can go wrong. There's never been a successful attack on Bitcoin itself. There's never been an attack on the network itself. So it is very resistant and has proven that over the course of almost 10 years. So it's been created a while ago, 2009. There was this paper by a person or people, that's very own little soap opera that we're not going to get into, about the creation myth of Bitcoin. It was created by means of a paper, of a scientific paper describing the whole idea of an implementation that actually did what the paper promised. And it is still the most successful cryptocurrency to date. So it's sort of the gold standard, if you want, of cryptocurrencies at the moment. It's still the most important one. Now, cryptocurrencies and cryptography, that sounds really bad, right? Because that's this weird stuff. Actually, no, it's very easy. For all the things that we need to understand about cryptocurrencies and bitcoins for this particular talk, at least, is all very, very simple. And I'm sure most of you know the basic ingredients here. We just need 2 or 2.5. The first one is the idea of a hashing algorithm. So if you've ever used something like that, for example, to hash some key, to put something into a hash map or hash set or something like that, you knowingly or unknowingly use the same thing, because a hash algorithm essentially just takes a piece of data and takes a look at that, or uses that piece of data to derive a value from it, and that value is sort of unpredictable. Well, actually, it's very unpredictable, because if you change a single bit in the input, the output will be completely different, right? So there is no way to predict what's going to happen in that particular output. This output is also always a lot shorter than the input, so it's like a fingerprint, like a small check that tells you you've put in the same thing, and it's also irreversible, so you can't get back from the hash to the original data value. So that should be very, very obvious, I believe, to most people. That's just a little math and a little computation that's happening here. Now, the interesting thing, and we're going to get back to that, is if I ask you to produce a specific hash, right? If I ask you, for example, to produce a hash that starts with 4 zeros, right? How would you go about that? How would you find out what input data you need to use to make that hash come out? Anybody shout something at me. What's the solution to this problem? Brute force. It's actually the only solution, right? There is no way, if it's a good hashing algorithm, there is no way to somehow, come up with a great strategy to do this. You may try different heuristics, but they're all equally probable to give you that particular value, and we're going to get back to that particular thing. But for the moment, all we need to know is that we have this piece of input data, we put it through this algorithm, and we get a hash value as the output. So that's ingredient number 1. Ingredients number 2 and 2.5 are something that you probably know as well. At least you know it if you've ever sent a signed or encrypted, or both signed and encrypted email. Right? So if we have something like a public and private key, we can, or if we create something like a private key, we can derive what's called a public key from it. And this is why it's called asymmetric cryptography, because if we have those two keys, then we're using different keys for signing and validating signatures and encrypting and decrypting it, as opposed to the same key, which would be sort of the obvious solution. And it's sort of similar to what I just explained. You can use a private key to sign a message. It's roughly similar. You get some piece of input data, you use the private key as a secondary input to a particular algorithm, and that'll produce a signature. But now the very cool thing, due to the mathematical relationship between the private key and the public key, is that I can validate the signature without having access to the private key. So if I have a private key, and if I keep it private, which is a very good idea, and one of the reasons it's called a private key, because you never ever give it to anybody else. If I have this private key, then I and only I can sign a message so that anybody else can validate it with a public key. That make sense? Hopefully it did, because hopefully you've done something like that. If you ever send an SMIME email, or actually if you ever used an HTTPS connection, this is something that happens underneath. There's some signing, some proof of identity, and some exchange of a encrypted key that's then used for symmetric encryption being used during every TLS connection. Okay, so that's sort of all of the cryptography we need. And now I'm going to go through all of this little universe of terms and technical terminology that's related to the Bitcoin network. And I'm going to try to make this brief because I don't want to waste too much of your time, but it's very important to me that you understand this stuff. So if you have any question, feel free to interrupt, and also feel free to add any comment. So if we look at Bitcoin, the first thing we can look at is the name itself. So Bitcoin itself, that's obviously the name of the currency, right? That's also the name of the system. It's the value. You can buy 1 Bitcoin. I have no idea what the current value is, probably lower than yesterday, or maybe it's gone up a bit again. I don't know, 4,000 euros, 3,500, something like that. So that's the value of a Bitcoin if you try to buy it in euros or US dollars or whatever other currency you want to have there. The next thing that we need to talk about is what's called a wallet and the related things. Now, people, when they talk about a wallet, tend to think that this is where your money is kept, right? This is where your Bitcoins are stored. That's not actually the case. A wallet is actually more like a key store. It is something that will create and maintain the keys for you. So a wallet is a piece of software. In fact, in the case of Bitcoin, and most others as well, but specifically in the case of Bitcoin, it's not a very complicated piece of software. So you're probably all programmers, or used to be programmers at some point in your career. If you spend like something between a rainy afternoon and a week, you'd be able to build a wallet software for Bitcoin. Because all you have to do is to grab some randomness from somewhere, like people moving the mouse or sampling some sort of noise or whatever. You need some real randomness. People can throw dice or something. And then you create private keys, and then from those private keys you derive what's called a public key and an address. Doesn't really matter at the moment. So you derive a few of those things, and then you can start using that wallet software to interact with the Bitcoin network. So the wallet itself keeps your keys safe. That should also give you a hint why it's not an exceptionally good idea to use an online wallet. Right? An online wallet of any sort would have to maintain your private key on somebody else's premises, which is something that you should never do. So don't use online wallets. If people have serious amounts of any cryptocurrency, what they typically do is they rely on either their phone's security, so if you have a decent phone, like one that you trust, maybe with an up-to-date Android or an iOS device, you can maintain a wallet software and the keys and the data that it stores on your phone. Or maybe you move to a specific device, like a hardware wallet of some kind. There are numerous devices that allow you to do that particular thing. Now, if the coins, if the values, if the money you have is not stored on the wallet, where is it stored? This is actually one of the reasons I in a very simplifying fashion and sort of half-jokingly call this thing a very slow database, right? Essentially, the whole network acts as your database. It stores the values. Whatever it is, whatever the kind of application is that you use on that blockchain will determine how data is stored and what data is stored exactly is stored, but it essentially maintains this whole piece of data in public. Unless you encrypt it, unless the system encrypts it in some way, which Bitcoin doesn't, it's readable by anyone. So in the case of Bitcoin, you have this giant database replicated across a huge number of nodes, including some client nodes, some full nodes, and some mining nodes that will maintain all of this data that's been exchanged on the Bitcoin network. Now, the keys in your wallet are exactly that. They are your keys for your particular data on that network. And nobody can use your money unless they have your private key. So if you keep the private key in your own wallet and don't give it to anybody else, you're sort of safe with the money that you provide there. Okay, so how do you interact with the system? What's the next step? You've written the piece of wallet software. You've interacted with it with some crypto library to create private and public keys and do some signing and stuff like that. Now the next step is to actually send a transaction to the network. So the Bitcoin network is composed of all of those collaborating nodes. It's a peer-to-peer network. Remember, it's supposed to be decentralized, so there is no central server that you interact with. Instead, you forward a transaction that you create to some node that you're connected to. So there's some discovery going on here. I'm not going to get into detail about that. But essentially, you compose a transaction, and on the Bitcoin network, a transaction is a transfer of money from one person to another person in a very simplified fashion. Actually, it's slightly more complicated because what happens is comparable to a cash transaction. You have a number of things that you got from previous transactions, like you have a number of bills in your pocket or in your wallet that you got because somebody gave you some money for some reason, or maybe you took it from the bank. Now, you can use that money to pay, so you can use the unspent outputs from previous transactions to pay for something. Let's say you have to pay for something that costs 30 euros, and you have two 20-euro bills. Then you would use those two 20 bills, and you would get back a 10-euro bill as change. So that is actually what's going to be reflected in that transaction. There are two inputs and there are two outputs. One goes to the recipient of the money, one goes back to you. In fact, if you leave, and you should, a tiny little bit unspecified, that'll go to the miner, which is one of the parties helping to operate the whole thing. So that's what's called a transaction fee. Now, the key thing here is that the transaction itself is valid in terms of only the person who received the money can spend the money. So when money is sent to someone, it's actually, in a slightly complicated fashion, stored in the transaction so that only the person with access to the corresponding private key can actually spend it again. So you could say the money is given to an address which roughly corresponds to a public key, and then only the person with the private key can actually use that money to pay for something else. So every transaction in itself can be validated in terms of, is this money that is actually the output of a previous transaction? And is it actually signed in the correct fashion by somebody who has access to the private key? That was slightly more complicated than the first thing, but I still think you're with me, right? Where we have those transactions. Now, what you can see in terms of the database qualities or the database requirements or characteristics is that obviously there's some order to the transactions, right? I can only spend what's been given to me before. So all of the transactions have an order. So you could argue that one way to store this whole thing would be as a long chain of transactions. That's actually not what's happening. What's happening is that transactions are aggregated into what's called a block. So a block is like a list or a set, or actually a list of transactions. It's a list of transactions that are treated as one thing to validate by the whole network. So think of how this might work. If you were to design this thing, you have a number of nodes. Those are all connected in this peer-to-peer fashion. And if I, as using my wallet software, send a transaction to one of the nodes, this node will propagate that transaction to all the nodes it knows. And those nodes will do the same thing. So within, let's say, a minute or so, a transaction on the Bitcoin network will be propagated to all of the nodes in the network, like a few thousand, a few tens of thousands of nodes. Now, some of those nodes will be doing what's called mining. And mining is called that because it's sort of the analogy to mining, let's say, gold, right? We're mining for something. What we're mining for here is Bitcoin. We're trying to get rewarded by getting some Bitcoin. Now, a miner does this by trying to find a valid block. I'll get to explain what that exactly means. Now, a valid block is something that aggregates a number of transactions. So to create a block, the miner will grab, let's say, 1,000 of those outstanding transactions that haven't been validated yet, and will try to build a new block of those 1,000 transactions. And once they found a block, they will transmit it to the network. Now, what does finding a block mean? Finding a block is actually an expensive operation. It takes some time to do that because there is work involved. And the kind of work involved here is computational work. Remember that little riddle that I showed to you with the 4 zeros and the hashing kind of thing, the brute force thing? So this is actually what happens. Imagine the block as a data structure that references 1,000 transactions, that references a number of other things, that references the previous block, that has some extra metadata. Then if you were to calculate the hash value of this particular thing would be some, well, not random, but some number derived from the data within that block, right? Now, if I ask you to make that start with a number of zeros, I have to give you a way to manipulate the data, but you can't just randomly manipulate the data. So this block includes what's called a nonce. That's a field that you can put any value you like into as a miner. So that's what miners do. Miners build a block, a semantically meaningful block, referencing valid transactions in terms of their cryptographic validity and signature. And then they start fiddling around with that extra random value. And they try inserting things, and they calculate the hash, and they check whether the hash starts with the required number of zeros. I'm slightly simplifying, but that's what's happening here. So the mining nodes, which are a certain specific kind of node here, actually have this extra task. They don't just relay messages, they also try to find blocks. Now, this is a time-consuming thing. It's also a pretty expensive thing, because to do that, you have to spend CPU cycles. You have to calculate something. You need to do that on fast and decent hardware. You need to expend energy. You need to buy energy and use the energy to drive this particular thing. To do that over and over again is an expensive thing, and it takes time, so why would you do it? You do it because you're allowed to include a transaction of 12.5 Bitcoin recipient yourself. 12.5 Bitcoin, as of today, is 50,000 euros. So if you find a block, you get the Bitcoin equivalent of 50,000 euros. That sounds kind of cool. It's actually pretty strongly related to the amount of energy and effort you have to spend to the whole thing, because you not only have to spend the energy to calculate the one block, you're not the only one doing this. In fact, all of the mining nodes all across the world do the same thing. They're in a race. They're competing with each other. Who's the first to find a valid block? The first one to find a valid block will immediately transmit that to the rest of the network and say, I found a block, hooray! And they'll pass it on to the next node, and the nodes will relay it. Now, if you're a mining node and you're yourself in the process of calculating and trying to find a new block, when a new block comes along, you have a choice to make. You could decide that, I'll ignore it. I'll just hope that my block will be done in 10 milliseconds, and then I can transmit my block as the new one instead. But depending on how much you believe in luck, you might just decide, well, okay, I'll throw away this block and try to find a new one. Because the blocks that we have here also form they also have an order, because every block refers to the previous block, which is finally why the whole thing is called a blockchain. Right. So the blockchain is called the blockchain because all of those blocks reference each other. And in fact, blockchain is not the perfect word. You could actually call it a block tree, because what happens is it'll fork at some points because people find new blocks in parallel and they now compete with each other. In theory, they could find another block afterwards, so you'll have like this branching thing. But actually, the branches are cut off very quickly. So in the Bitcoin blockchain, you typically get those 1 or 2 or 3 level deep branches. But if I, as a mining node, or in general as a node, receive a block, I will, and I already have a competing thing, I will simply pick the longest chain. So the longest chain will win. And that is what's called the Nakamoto consensus protocol. So it's combined of those two things. The whole system, the worldwide system, gets to a consensus because it takes time and effort to build a block, so that makes it a sort of expensive thing. And there's also a defined way to agree again to something. Everybody with me still? Any question? Please, go ahead, it's fine. No question right now.
Yeah, we have catch boxes.
Yeah, you can throw. I'm very bad at throwing. You'll have to throw for me, but if you raise your hand...
Do you have questions, anyone? I can throw it at you. You can ask it loud.
Okay.
No?
Otherwise, I'll continue, no problem. Okay, so why are we doing this? That sounded like a mildly interesting, technical, complex thing. Why would you do any of that? Now, that's really an interesting question. Why do we do this? The very cool thing is that the Bitcoin network is open to anybody. So when I said that you, on a Sunday afternoon, could write your own wallet software, I was meaning that in a literal fashion. You can do that. And you can start participating. You don't have to register. You don't need a credit card. You don't need anything. You can just start participating in the whole thing. Let's say you're doing some work for somebody and they pay you in Bitcoin. You don't need to have a bank account. You don't need to have a credit card or anything of the traditional banking system. It's completely own, self-reliant system. And the next cool thing is that I can trust it, which seems really weird. Why would I trust this complete bunch of strangers with anything? Why would I trust a mining node? And that is actually a very interesting thing. The original Bitcoin paper combined a number of things. It had a decent programmer, so it had interesting computer science. It had very decent cryptography. Not easy to build something like that without it being broken down by cryptographers in like 10 seconds. So this person knew what they were doing. But it also included a lot of game theory and economics, because the really cool thing is it's not worth cheating. Because imagine what you would have to do to cheat. So what does it mean to cheat on a blockchain or on the Bitcoin network in particular? Cheating would mean you spend somebody else's money. Well, you can't do that because somebody else's money is protected by their private key. Unless they're negligent with their private key, you have no chance to get access to the money that belongs to them. So what can you do? You could try to forge history. You could try to create an alternate version of history. Now imagine what you would have to do that. Let's say you want to exploit what's called the double spend problem. That is, you buy a house and then you use the same money to buy a Ferrari. And you can spend the same money twice because you simply erase the history of you having bought that house and you use the same money again. Now, depending on where the transaction of you buying the house sits in the blockchain, you have to expend the energy and the computing effort to recreate all of the following blocks. Does that make sense? Let's say your transaction is here and there are 10 blocks afterwards. So to cheat, you would have to create an alternate version of reality that started 10 blocks back, and you would have to calculate the hashes for the blocks that build on top of each other to create this alternate version of reality, while the rest of the world is fancily going on computing new valid blocks. Which means that cheating is much more expensive than playing by the rules. Which is why if you have access to this type of hardware and to the type of energy and you're willing to spend this, you'll get a much better reward if you simply mine Bitcoin. Which is sort of an ingenious solution. It addresses the motivation of people of why they would cheat as opposed to trying to solve it with a purely technical means. Any question now? Okay, good. So you all know this, or you're very shy. It's fine. So how would you go about that? So originally there used to be the case that you could use some sort of CPU to do that. So I have friends who used to mine Bitcoin on their laptops. Unfortunately, some of them have lost the private keys, but don't ask them about this because they get really sad. You can no longer do this anymore because these days not even a GPU, which is a graphics processing unit, is good enough to mine Bitcoin. Not even an FPGA, which is a field programmable gate array, is something that's like sort of a semi-hardware, software programmable CPU thing is good enough. What you need these days to mine for Bitcoin is an ASIC, which is a specialized processor built for mining Bitcoin. It's actually worth doing that. Actually, Bitcoin mining has driven innovation in terms of getting more performance out of hardware because it's such a good business model, right? And there are rumors, nobody really knows if they're true, that some of the people who built these highly specific ASICs don't sell them because it makes them more money to use them to mine Bitcoin than to sell them to somebody else to mine Bitcoin. So it's really an interesting market here. You could argue that these things go from a very generic to a very specific thing. It all depends on the hashing algorithm. So Bitcoin uses this particular thing, but there are other blockchains. We'll get to that in a second. Like they use other algorithms, and some of them are more resistant, and some of them are less resistant to this whole ASIC thing. And I'm not going to get into too much detail about this, but you can see that there's a specific explanation that I gave you for Bitcoin, but it's roughly similar in many other blockchains. They use other algorithms. They don't use this find the number of zeros or match the number of zeros at the beginning. They use other algorithms, but it doesn't really matter. It is the same thing. So we expend computing power, hashing power, and energy to create these blocks, which means we can trust the system. So you could argue we create trust by spending energy. Now, of course, there's another view on the whole thing, which is we're actually doing something very bad here. And that is, to me, the most important criticism right now of the whole blockchain thing, specifically the Bitcoin network. Now, personally, I'm still undecided as to what I believe here. So I've created 2 slides giving you the option to make up your own minds of what you want to believe and what you think. So here's the first one. The position 1 is, this is a catastrophe, right? We are ruining our planet for nothing. There's no point in all of this, right? So go home. You're in the wrong talk. Go to another track, talk about, or listen to somebody talk about something meaningful. Because if you take this position, then people will argue that we have this continually increasing demand, and last time I checked, the Netherlands used something like 106 terawatt hours of energy per year, whereas the Bitcoin network used 65. Is that a good relation? Is the value of the Bitcoin network related to this number in a meaningful fashion compared with a nation state? Right? That seems like completely off, right? It seems completely crazy. Why would anybody want to do that? Because if you look at it right now, it has little to no value, right? It's just speculation. People make money or lose money, or it's not serving society in any meaningful way, and I have to agree, at the moment, the Bitcoin network specifically is not really used for the purpose it was originally intended for, which was to make payment very easy. It's used for speculation, right? That's what people do with it, because they hodl to the money that they have there. Don't worry. Right, so, yeah, or they sell it, or they try to make, or they lose money, or whatever, right? You could also argue that it makes it very useful to buy cheap, dirty energy and waste it to create blocks because you'll get rewarded in this stupid currency. So you can see people get really, really angry. So my recommendation is, if you're at a party and if you like Bitcoin, don't let everybody know, because you might not be a very welcome guest. In addition to this, and that's why I showed this previous slide, you also have the hardware that you created, right? You have all of those ASICs. They're completely useless unless they mine Bitcoin, because they've been specifically created to mine Bitcoin. So you have all the overhead of creating this particular hardware as well, in addition to the energy that you invest here. Right? So this proof of work thing really might be something really bad. If you ask me, if we stop Bitcoin today, I would agree that it's been a waste of time so far. But give me a second, and then, is that okay? But you could also view it from a different perspective. Now, this is the other view, which I consider just as valid. It's basically, this is all no big deal. Because, first of all, it's completely wrong to assume that demand will increase linearly. So if it's at 65% of the Netherlands today, that does not mean that double the size of the Bitcoin network will be at 1.3 Netherlands, right? It's definitely more useful than Christmas lights. It's hard to argue with that, right? We waste energy on a lot of stuff, and that's one example where we waste way more energy. You could argue that one of the downsides here is that the cost is so transparent. You can see it. Well, actually, you can't. In fact, if you look at the energy consumption index, that's what it's called, it comes from a single block by a single person. He's doing a good job, but it's just one source, and there are other people who argue differently. But okay, even if you try to do more positive calculations, you end up in the roughly same ballpark, so it's perfectly okay. But it's still way more obvious than all of those skyscrapers that have been built, that are lighted, where people use their cars to go to work every day, and all of the data centers operating our financial system. Who knows what consumes more energy? At the moment, Bitcoin is not disrupting that. Because, and I need to mention that because I had slow in the title of my presentation, if you do the reverse calculation, you'll find out that having 1,000 transactions in one of those blocks and having a block every 10 minutes gives you something like 3 or 4 or 5 transactions per second on the Bitcoin network, which isn't really that impressive. So it's not competing with anything right now in terms of financial system, but it's still using a lot of energy. But it makes it very transparent. Another aspect is you might argue that you don't need multiple proof-of-work chains. At the moment, we have the problem multiple times, but you could have one of them. There are also alternatives, which we'll get to in a second. You could also argue that this is a perfect chance to use cheap and clean energy, because you can do the validation somewhere where energy is produced in excess and can't be used anyway, or it could be done in countries where energy is very cheap because it's built using not fossil fuels or anything like that, but using, I don't know, somewhere in Iceland or so using thermal energy, whatever. And you could also argue that we're going away from those ASIC-reliant things and make the hardware problem go away. Now again, which one of those two you buy into, I don't want to tell you. I'm undecided. I have a bad feeling about the amount of energy used in the Bitcoin network. I don't like this fact that it's so much. I think this should go down. I also like exploring the alternatives. But I also don't think it's worthless, because the fact that it has this trust thing built into it just purely in a computational fashion is a very, very interesting property, and we're paying for that anyway. It's just not that obvious in other regards. So did I answer your question already, or do you want to add it?
No.
Okay, please.
Oh. Sorry. Can I give you a catch box?
Whoa!
Oh my goodness. Give that man a round of applause. So one of the biggest problems that I see with Bitcoin is the fact that there's a limited supply that can ever be mined. And even with the rewards, the 12.5 Bitcoin, which is a lot of money, you still have very low transaction rates. What's going to happen when we hit the 21 million and all of a sudden those big incentives for actually mining the Bitcoin and making that investment, once you hit 21 million, you're done?
Well, so the thing you're referring to is the fact that the amount of Bitcoin is limited specifically in the Bitcoin network, and this reward is being halved every few years. I think every couple of years it goes down. So it used to be 50, went to 25, went to 12.5, will go down. We can see that it'll approach 0 at some point in time, so there'll be no benefit in mining anymore, unless you count in the transaction fees. So the miner not only gets the reward, the miner also gets this transaction fee that I mentioned. So obviously the transaction fee of all the transactions included in the block will have to be high enough for a miner to make some money. This is really a market function, right? Is it worth spending that amount of money? So this is all done in a very interesting fashion. Actually, the network itself recalibrates itself in terms of the complexity of the riddle to be solved. So it roughly takes 10 minutes to find a block. If the system as a whole figures out that it doesn't take 10 minutes, it starts approaching 5 minutes, then it'll make the riddle more complex. And it'll do the same thing if it finds out that it takes too long to take a block. So depending on the amount of energy and computing power people are willing to spend on the whole thing, this will readjust. So I can very well imagine that at some future point in time, it'll make much less sense to spend so much effort on mining, so it'll be less, which is maybe a good thing, because it'll reduce the energy problem, right? So you can argue, that's actually what the dig economist, this person doing the calculation about the catastrophic energy consumption, is doing. They're calculating the actual benefit that people get from mining a block. And then they're using that. This is concluding or judging from that. This will be the amount of energy that they will be willing to spend and still make money. So they will spend it. So a high value of a Bitcoin means that you will spend a lot of money, which means a lot of energy consumption. If a Bitcoin is worth $1 or €1, then this problem would not be that bad. Again, you can also argue that the transaction fees are going to be so ridiculously high that nobody can do what's a microtransaction anymore. So you can only use it to exchange thousands of dollars. To which you can also argue, yes, but it's just as cheap to send $1 million or $100 million as it is to send €1, which is not something that can be said of the current banking system. I don't know whether you've tried to send 100 million euros. I haven't, but I hear it's not that easy. Okay? Good. So that was Bitcoin. So the essential thing here is Bitcoin is the inventor of the whole thing, or it's the originator of the whole thing. It is still very much there. It's still very much valid. It's still a good choice if you want to learn about how the whole thing functions. But it's a very specific blockchain because it has one purpose and one purpose only, which is cryptocurrency. It's a blockchain built for exchanging money, for doing financial transactions. Actually, Bitcoin has something that's called Bitcoin script. I'm not going to go into too much detail. I just want to very briefly mention that Bitcoin has this very limited scripting capability that is in fact used even when you do a basic transaction. To make this long story very short, actually this signature thing, actually what's happening is the transaction has a little script that as its input needs something that can only be created with your private key to unlock the money that's in the unspent transaction. But never mind, it doesn't really matter. There is a little bit of scripting going on that you can, for example, use to build something like a transaction that requires multiple senders. Let's say you inherit money. You and your siblings inherit money from your grandparents, and so only the 3 of you or the 4 of you jointly can spend that money on something. That would be something that you could build with Bitcoin script. It's a very limited language. It's comparable to Forth, if you know that. So it's a stack-based language with. It's not Turing complete, so you can't do a loop, you can't do a jump, you can't have an endless loop. Most importantly, you don't have to solve the halting problem for the whole thing. So Bitcoin has this, but it's very limited, and there's a good reason for that because very limited scripting reduces your security risk drastically, and Bitcoin has a very good history of being secure in itself. But it also sure sounds interesting to be able to program a blockchain and to do things other than financial transactions, right? If you could do cool things with a blockchain, that would be kind of awesome. Which is essentially why somebody took the idea and created this thing. Now, Ethereum is the second best known public blockchain around. Not only public, but mostly known for its public thing. And it's very similar in many regards. So it has this blockchain approach. It has its own currency called Ether. It also creates blocks, does it a little faster, not 10 minutes, but 1 minute. Has this proof of work thing, plans to change it, going to go into that. But the most important thing here is it's a platform for what's called a contract, for arbitrary contracts. And a contract is nothing but a script. Right? A contract is a program. So Ethereum is a programmable blockchain that allows you to deploy programs onto it. And those programs are little object-oriented scripts that can maintain state. And the state, of course, is maintained in the blockchain as well, right? So you have 2 kinds of contracts, or 2 kinds of possible recipients or senders on the Ethereum network. You have what's called an externally owned account. That's very similar to what we just talked about with Bitcoin. So you can own Ether. You have your own Ether address or Ethereum address that I can send some Ether to, and then you can use that to buy something or exchange it to Bitcoin, whatever, right? You can do interesting stuff with the money. But you can also create an entity based on a contract, and that's what's called a contract account. Now, this thing will be able to receive money, and what will happen is determined by what method you send that money to. Does that sound weird? So imagine an Ethereum contract is a class with a number of methods, and you can invoke one of those methods. And then what will happen is determined by the code that method is implemented with, right? So when you want to create an Ethereum contract, you write a program in one of Ethereum's programming language, most likely the language called Solidity, which is a JavaScript style typed, slightly weird language. And you can use this language, you can test it locally, you have nice tools to do that, and then this little program maintains its own state, like a balance in some account or some participants, a registry of collaboration partners, whatever it is that you want to express in that particular program. And then when I want to, can send some money to one of those methods. I can invoke one of those methods, and I can, well, I don't even have to send money, I can also do something else with it. I can invoke one of those methods and have it do certain things. which is pretty cool, because this is essentially what we've been doing with contracts, that's why it has this name, for a few centuries, right? So when you do business with some business entity, you agree to some general terms, or you maybe have a real contract signed by both parties that specify what the respective duties and obligations and things are that you receive in return, right? So I will send you 100 euros every month. You can do it with whatever you like, but I require to get 2% interest. That's sort of the contract that we have here. And it can be anything else. It can be I'm allowed to have access to your streaming archive of video files in return for 10 euros per month. Right? That's the sort of contract that I typically do when I sign somebody's terms of agreement. And here, it's essentially done using code, which is pretty cool. There's one very interesting thing here, which is the fact that to have that code run essentially means that all the miners will run the code now, right? So everybody who wants to validate, wants to create a block has to create the state changes based on the transactions, because those transactions are now customized using the scripts. So why would anybody run code that I sent to them? Are they not completely crazy, right? I could hurt them with the code that I run there. Well, actually, it's sandboxed, like with a JVM or a CLR or WebAssembly or something like that. But it also has what's called gas as a concept, and that essentially means that you send a little payment to drive the machine along with every method invocation, and that gas gets consumed with every instruction, right? So every instruction that this Ethereum global virtual machine does consumes a little bit of the gas that you send, so your program will only run for as long as the gas that you send with it allows for it to run. So that's how they make sure you don't run out of computation power or don't hurt the system. Make sense? So that was like a 3-minute introduction to Ethereum. You can go to an Ethereum conference easily with 5 parallel tracks. In fact, I was at one and spent 3 days just talking about Ethereum. So this is perfectly fine if you don't get everything of this, but the general idea of having a programmable blockchain might be appealing to you. Now, those were both public things, right? Public blockchains, well-known public blockchains. But we have alternatives. So some of the alternatives are private permissioned ledgers. They're using essentially the same thing, but they're not open to anybody. Ethereum and Bitcoin, anybody can participate. With a private ledger or permissioned ledger, you limit the people who can access the whole thing. So you might use it with partners, right? Like, for example, you're a consortium of banks and you want to create a blockchain for those banks to collaborate. And then only somebody who has gone through a complicated onboarding process and spent €1 million will be able to participate in that whole thing. There are lots of companies supporting that whole thing. There are open source alternatives doing that. I'm not going to get into it, just want to mention this is kind of very important other option of doing that. There is an option of combining chains, it's what's called a sidechain approach. That will mean that you have different blockchains with some sort of relationship. So for example, it might be that in one blockchain you create a transaction that lock a certain amount of money within that blockchain and sort of transfer ownership or usage rights of that money to another blockchain. And then something will happen in that blockchain, maybe using another consensus algorithm, maybe using a faster consensus algorithm that will allow you to come to decisions quicker, maybe less secure, less trusted, but then will sort of anchor back into the original blockchains, like a two-way relationship, a bidirectional relationship between blockchains to achieve something like that. And you can generalize that to a sort of hybrid approach, which is actually what basically every useful application of a blockchain is these days. So the blockchain, even the Ethereum blockchain, is slow. It's really, really, really slow. You can trust it, but it's slow. Even if it's run on company premises, if it's using a distributed system across company boundaries with some cryptography going on, it's still much slower than a centralized database would be. Which is why many people combine things. So you have some sort of application. This can be anything you like. It can be any sort of centralized, decentralized, split peer-to-peer kind of thing, whatever you like. And it's connected to a blockchain, but it only does very, very few things in the blockchain. So one of the probably best rules for using a blockchain is use it as little as possible, which sort of generalizes to if you don't need it, don't use it, which I very emphatically agree with, right? So a blockchain is something that's supposed to be used for a very, very specific use case. If you don't have that use case, don't use a blockchain. If you hear somebody who tells you use a blockchain without listening to your problem first, you know they're not a good person to listen to, right? So you'll have those hybrid things most of the time. Okay. So I wanted to leave some room for questions. So I've done this very, very convoluted summary slide here. So there are some very good things about a blockchain. A blockchain, specifically a blockchain using the much hated proof of work algorithm, is of today the only solution for a particular set of problems. If that is a set of problems that you have and that you want to address, then this is the only thing you can do. There is nothing else in the world that will allow you to, in a decentralized fashion, open to anyone, censorship resistant, trusted, give you any chance to create something comparable to Bitcoin. If there were, it would exist. Nothing like Bitcoin exists using other technical approaches as of today. Might change tomorrow, but at the moment that is correct. That does not mean at all that I'm a Bitcoin fanboy, right? I'm very skeptical about some of the social things, economic things, global, political things. It can be that, but still, technically, it is an extremely fascinating approach. It's fascinating technically because I've had 45 minutes, so I've only really scratched the surface of a lot of stuff. And I'm happy to talk about more things afterwards if you want to. But there's a lot to discover here, a lot of interesting things, so it's fascinating technically. It's also extremely fascinating from a business perspective. Because if you look at the ways decentralization can change things, it's really, really hard to come up with good ways to incentivize people to participate. It's an interesting thing in constructing those business models that would benefit from something like this. Either permissioned, non-permissioned, trusted, or somewhere in between. It's a really fascinating thing. And that's the good part. That's why I like playing around with it. And that's why I'm not going to become a vendor, because I could then only do this thing, which I would hate. But as being it being one part in the arsenal of things to look for is really nice. There's some bad things. I mentioned that it's kind of slow. It's also applied to almost anything without thinking, right? So many people, especially non-technical people, now think blockchain means using computers, right? So they have this horrible thing that they haven't automated yet, that they do manually, and now somebody tells them, well, we can finally digitize that, we can finally automate it, we just need to use a blockchain. And most of the time, it's not the blockchain that they need, it's some decent, modeling and thinking and architecture and plain old software development would have done the same thing. Specifically, if there is a central authority. If you have a centralized thing sitting there just waiting to run a centralized database, then do that by all means. Don't use the blockchain stuff. And you can also, depending on your views, this is, again, a very long discussion, you can think the ugly stuff is that it's hyped like crazy. Interestingly enough, in a way that I haven't seen before, typically you have something that is hyped, this Gartner hype cycle kind of thing, right? It's hyped. At the height, everybody thinks this is the greatest thing since sliced bread, and then it goes down into the valley of, disillusionment, the trough disillusionment. But in this particular case, we have both the hype and the anti-hype, both at the absolute top. So people hate it with a passion and love it with a passion. It's really fascinating. I haven't seen that before. It's wasteful with energy. We talked about that, depending on the particular algorithm. There are alternatives that I didn't have time to talk about. And you could also argue that the fact that it can't be regulated is a very, very bad thing. It all depends on your personal and political views, and it's also a very, very complicated issue to talk about. So that's all I have for now for the talk. Thanks a lot for listening.
Okay, actually I can see that one guy is typing a question in Slack, but maybe you can ask it with the catch box. Who's that? Okay.
Several people are typing.
Oh yeah, I'll probably read it then. So what is the current state with proof-of-stake algos?
Yeah, so proof-of-stake is an alternative to proof-of-work. So proof-of-work is the stuff that I described, doing this brute force thing over a course of time to come up with a newfound block. And the thing here is that everybody can participate. So every miner does the same thing. Now, it would be much nicer if you had a smaller group of people that would just take a vote, right? You have this 10,000 nodes, and you just pick 50 nodes at random and let them have a vote whether or not this is a valid block. And if your randomness was good enough, then that's going to lead to the same result. That sounds reasonable, right? But how do you pick those 50 nodes? How do you make that decision? And one way to get to that smaller group is to use proof of stake, which is they prove that they have a stake in the system. Like, I'm betting this 1,000 Ether, and I'm risking them. I'm putting them here. I'm putting them in sort of a locked account, these 1,000 Ether, and then I hope that I'll be selected for the vote. As a result, for doing my duty during the votes, I get back 1,020 Ether, so I make a little profit. But if I cheat, and if the others find out that I cheat, I lose my 1,000 Ether. So I've proven that I have a stake in the system, and that's important. It's in the system. It's not outside of the system like with the energy proof. It's within the system. And that sort of creates the assumption that because I'm willing to do that, it would be really stupid for me to cheat, because I would lose the money and I would also devalue the whole system. So that is sort of the assumption. There's a very, very, very simplified explanation of the whole thing. But roughly like that is how the proof of stake variants work. There are numerous variants in numerous different blockchains. And the most important one to switch to one of those very soon now is Ethereum. So at the moment they're exploring a hybrid model, but they expect to move to proof of stake pretty shortly to reduce the energy consumption and to get it to get out of this thing. It's also a matter of scalability, obviously, but again, that's another challenge, another topic to explore.
Well, we're kind of running out of time, but we have one more question in Slack. Do you have examples of new, interesting, or successful business model that blockchain has created?
So I had one very simple business model. Maybe it's not exciting, but I found it very down to earth, which was with a company, with an insurance company in Switzerland that we didn't work for them, we talked to them, and they have created something for reinsurance. So if you know the reinsurance model, it's the kind of insurance that an insurance company buys, a very B2B kind of use case. So the insurance companies, among another, have this relationship of a shared risk. So somebody insures a risk but needs somebody else to cover that because they can't cover it alone. And that's a wonderful multi-party kind of use case. It's also something that they didn't want to centralize because that would have meant that they would have to agree on who does that. So they would maybe had to found somebody and then give them money to run and operate a centralized thing, which is not something that they wanted to do. So what they did instead was they created their own private permissioned blockchain. Everybody gets a set of Docker images that they can run on their own premises or Google or AWS, Azure, whatever. And then this it's actually a private Ethereum thing, and it can use proof of authority, which is another option. You just prove that you say who you are because you've been onboarded before. Right? They can only do that in a permission chain, and they use that very happily. So I would have preferred if they did it doing parts on the public Ethereum thing, like the registration and onboarding, because it would have been slightly more open, but it's still, I think, a very down-to-earth, nice use case that I can think of. And if you want to look for fancy use cases, just look at any of the 5,000 companies that got 50 million euros in funding recently, so it's amazing how many people are doing crazy shit with the whole thing. So, thanks again. Have a good conference.
Yeah. Thank you very much. Thank you very much, Stefan.